Hey, today's the last lesson in our BC topic on indeterminate form and using L'Hopital's rule. So you may be familiar with the L'Hopital rule cases that we've experienced in Calc AB, where we had 0 divided by 0 or infinity divided by infinity. We knew if we got those conditions that then we could use L'Hopital's rule directly. But today we want to look at the other 5 cases, so we have 7 cases in all where we have indeterminate form. And like I said, case number 1, that was 0 divided by 0 and infinity divided by infinity. We knew right away we could use L'Hopital's rule when we had that condition. This lesson will be divided up into all 3 cases. So case 2, that would be these 2 cases when you have 0 times infinity, or you have infinity minus infinity. So those are a little more difficult. And our object is going to be to rewrite these types as a fraction. And if we rewrite them as a fraction and test our limits, then we turn that into a case 1. And right away, we can use L'Hopital's rule. And then at the end of the lesson, we're going to see that we have the 3rd case. And the 3rd case is the more complicated of indeterminate form. That's when we have 0 to the 0 power, infinity to the 0 power, and 1 to the infinite power. And like I said, these are a little more complicated. So in this strategy, we're going to use an e to the ln x to the x trick. And that way it'll give us a chance to write that as a fraction, which would lead us to case 2. And then we could use that as a test for case 1, L'Hopital's rule. And that way we could go back to L'Hopital's rule, because we could turn it to case 2, write as a fraction once we get to case 2, and that would lead us to case 1, and then we would use L'Hopital's rule. So that's how indeterminate form is broken down in my mind. So without reading all the extras in the notes, let's think about those 2 examples at the beginning. What do you remember or recall? So the limit at infinity here, if we tested out the limit as x goes to 3 for the numerator and tested out the limit as x goes to 3 in the denominator, we're going to find out that we have 0 and 0. So when we have 0 over 0, that was the reason to use L'Hopital's rule. But you could also, if you wanted to, recognize right away that by factoring the denominator, you could remove that problem at 3, and then you could just evaluate the limit again, and that limit would be 1 over 6. In Calc AB, we called that the factoring technique. We also knew from maybe back as far as Algebra 2 that when you saw the numerator and denominator were the same, that you could just take the ratio of the coefficients and knew right away that our boundedness was at -5 when we went to positive infinity. But you could also use the algebraic technique that what we called the dividing out technique, where you divided the numerator by the highest agreed term in the denominator and worked through that situation, and then did the same thing in the bottom, divided the denominator by the highest agreed term in the denominator, and we would have ended up with 0 plus 0 minus 5 divided by 1 minus 0, and that would lead us to -5. So those were called the factoring technique over here for A, and the dividing out technique over here for B. So those were the approaches we used back in Calc AB. And here's those rules again. Whoop, I went too far. Here's those rules and those methods again. And here's our restating L'Hopital's rule. Now remember, we want to show for our AB and BC exam that we need to show the limit at the numerator and the limit at the denominator separately for our exam purposes. And I'm restating that here. This is for our AP exam. Write the limits of the numerator and the denominator separately. Then you can use L'Hopital's rule. So let's take a look at that, how that would look on a free response type question. So the limit as x approaches 1 for natural log of x is 0. And the limit as x approaches 1 for x minus 1 is also 0. So here we've stated those two facts. The limit of the numerator is 0. The limit of the denominator is 0. That's case number 1 when we have 0 divided by 0. So we're going to employ L'Hopital's rule and rewrite that as a fraction this way. So the derivative of the numerator is 1 over x, and the derivative of the denominator is 1. And now when you apply L'Hopital's rule, we have 1 divided by 1, and case solved. For example 3, showing the same approach as example 2, we want to check the limit at 0, the cosine of x. So the cosine of 0 plus 3 times 0 minus 1 is going to be 1 plus 0 minus 1 for 0. And the denominator, obviously, is also the limit of 4x at 0 is also 0. We have 0 divided by 0. That's indeterminate form. And now we are knowing that this is case 1, and we can use L'Hopital's rule. So taking the derivative of the numerator, we're going to have negative sine x plus 3, and the derivative of the denominator is 4, and then testing our limit at 0, the sine of 0 is 0 plus 3, and 3/4 is our limit by L'Hopital's rule. So this was case 1. Those were the easiest cases. And let's take a look at example 4. It may well be case 1. So we have the limit of e to infinity, that's infinity, and the limit of as x approaches infinity of x squared is also infinity. Likewise, this is infinity over infinity, and that's case 1. We can immediately use L'Hopital's rule. The derivative of e to the x is e to the x, and the derivative of x squared is 2x. But again, if you apply the limit at infinity for e to the x, we're still infinity over infinity for the numerator and the denominator. That's still case 1, so we can apply L'Hopital's rule a second time. And the limit at infinity of e to the x is going to be e to the x again, and that's infinity divided by 2, which tells us that the function is unbounded in a positive direction to infinity. So this was still case 1, but we applied L'Hopital's rule twice in this case. Now you might want to turn off the video and try this one on your own. Then come back and join us to see that you got the same result. And then testing the numerator led to infinity. Testing the denominator led to infinity. This was indeterminate form, which allowed us to use L'Hopital's rule, taking the derivative of the top and the bottom, and then applying the limit at infinity led us to 4/3. In example 6, we are looking at x approaching pi. So the sign of pi, if we tried direct substitution, the sign of pi is 0, and 1 minus the cosine at pi is going to be 1 minus negative 1. So we're going to end up with 0 divided by 2, and that's not an issue. It's not indeterminate form. It's an okay situation with the numerator being 0 and the denominator any real number. Our limit at pi is 0. And then example 7, the last one in this section, the limit at infinity for natural log of x is infinity, and the limit at infinity for the square root of x is also infinity. Again, this is the case 1, infinity divided by infinity, so we can employ the L'Hopital's rule. Taking the derivative of the numerator is 1 divided by x, and the derivative of the denominator is 1 divided by 2 square roots of x, which simplifies to be 2 divided by the square root of x, and substituting infinity or a very large number, the square root, 2 divided by the square root of a very large number is going to lead us to 0. So you just have to be careful. Here we are, we're going to look at case number 2, where we either have 0 times infinity or infinity minus infinity. And we're going to look at how to apply L'Hopital's rule in this section. So we're going to, if you notice the little tip down here, we're going to rewrite that as a fraction. So here in this case, if you apply the limit as x goes to 0 from the right, we have 0 times infinity. And again, if it was on the AP exam, I would need to show that I've got this limit being 0 and then the limit for the second function, natural log of x, being infinity. This is case 2. So I want to rewrite it to be able to rewrite it as a fraction. And this is kind of like a little algebra trick. So as x goes to 0 from the right, we'll write the natural log of x divided by 1 over x. And then this is going to lead us back to case 1. So when we try the limit at 0, so we want to look at each piece. And I'm trying here to model what you would do on the AP exam. The limit at natural log of x is at 0 is going to lead us to negative infinity. And the limit as x approaches 0 for 1 over x is also going to lead us to infinity. So we have infinity divided by infinity. That's case 1. And we're going to go back and use L'Hopital's rule now. So applying L'Hopital's rule applies since we had case 1 over here. The derivative of natural log of x is 1 over x, and the derivative of 1 over x is negative 1 over x squared. And now, simplifying this piece one step further before we apply the limit, we're going to end up with negative x, and substituting 0, our limit is 0. So this one's a little more complicated. When you have this type of indeterminate form, our object is to rewrite the original problem like a fraction. So I rewrote x as 1 divided by x. Applied the limit at 0. That gave us indeterminate form like case 1, the infinity divided by infinity. Took the derivative of the numerator and the derivative of the denominator, simplified it, and then applied the limit at 0. So like I said, these are a little more complicated. Then in example 9, you may want to turn off the video and give this one a try by yourself. And then come back to see that your work matches my work. If your work looks like mine, you found out that the limit on the first part was infinity and the second part was 0. So we had case 2, infinity times 0. So anytime we have case 2, we want to rewrite the problem like a fraction. We move the x to 1 over x in the denominator, and then checking the limit at infinity on the numerator led to 0. Checking the limit at infinity on the denominator led to 0. So this gave us L'Hopital's rule. Now we're back to case 1, taking the derivative of the numerator and using the power rule and the chain rule for the derivative of the exponent, and then taking the derivative of the denominator allowed us to cancel the common factors, and then we can apply the limit at infinity for the remaining factor, e to the 1 over x, so that gave us e to the 0, and at infinity the limit was 1. So these are a little tricky. And then we come down to limits of differences. So this is again case 2. And when you have the limit of a difference, we're going to approach this as getting a common denominator and turning that into a fraction. So here we first want to show that, just to save time, we want to show that we have infinity minus infinity, and I saved that work for you. And after we show that we have infinity minus infinity, then we want to turn this into a single fraction. And by turning that into a single fraction, I'm getting a common denominator, and that's going to be x times 1, and then negative 1 times e to the x, and negative 1 times negative 1, and then multiplying the denominators together, x times e to the x minus 1. And then again, saving for time, our next step on our paper would be to show that this leads to indeterminate form. So you would need to actually write that out on your paper to show that the numerator leads to 0 and the denominator leads to 0. And when that occurs, then you're back to case 1 and you can apply L'Hopital's rule. So using L'Hopital's rule, I believe we may have to do it again. So the numerator, derivative of the numerator is 1 minus e to the x, and thinking ahead, if you apply that derivative is applied at 0, the limit is 0, and if we take the limit of the derivative of the denominator, this would be x e to the x minus x, so this derivative would be x e to the x plus e to the x minus 1, and substituting 0 there would also give us 0, so we could show that L'Hopital's rule the first time is also indeterminate form, and we want to use L'Hopital's rule again here. And this was the derivative of the numerator, so we want to apply the derivative of this derivative, which is negative e to the x, and then this was the derivative, so we want to take the derivative of this. That's first times derivative of the second plus the second times derivative of the first, which is 1, and then the derivative of e to the x, so that's going to give us 2 of those, and then substitute 0. So we have negative e to the 0, which is negative 1. And this is going to be 0 and 2 times 1. So our limit is negative a half. Lots of algebra. You just need to be careful. And then finally, again, your job on paper is to show that you have the indeterminate form of infinity minus infinity. And by doing that, we want to get a common denominator and rewrite this as a fraction. And if you think about secant as 1 over cosine and tangent as sine over cosine, then you can use those properties of trig identities. Got a common denominator. Cosine's my common denominator. Put those together. We've got the limit approaching pi over 2 of 1 minus sine divided by cosine. And let's see, what's that going to give us? 1 minus sine, if we test the limit at pi over 2, we're going to show that you end up with 0 divided by 0, which is L'Hopital's rule from case 1. We've turned a subtraction or a difference problem into a common fraction with a common denominator tested at pi over 2. 1 minus 1 is 0, and the cosine at pi over 2 is 0. This is case 1. You're allowed to use L'Hopital's rule. And taking the derivative of the numerator is negative cosine, and the derivative of the denominator is negative sine. And then applying that rule, at cosine you have 0, and at sine of pi over 2 you have 1. 0 divided by 1 leads us to a limit at 0 as x approaches pi over 2. Then finally, at the end of the lesson, these are the 3 harder types of indeterminate form. And like I said, they don't show up very often. We're looking for 0 to the 0, infinity to the 0, and 1 to the infinity. And we're going to apply those limit properties using some tricks with the e to the x, one of the properties of exponential functions. Okay, example 13 is another challenging one. And we can show that the limit of the numerator at 1 is 0, and the limit at 1 in the denominator is also 0. This leads us to case 1. We're going to use L'Hopital's rule, taking the limit at 1 for the derivative of our numerator. The derivative of the antiderivative, those cancel. You might remember from the fundamental theorem, this is e to the n squared times the derivative of the upper bound. And then the bottom derivative is going to be negative 1. And if we took the limit at 1, so taking the limit of negative 1 e to the n squared times 2n, or 2 to the n, got to be careful how I'm writing that, 2 to the n, not 2n, oh yeah, taking that limit, that's going to be negative 2, and then 1 squared, it's going to be negative 2e. So we're good to go there. That's the easy way to apply that one. Example 14, this is the example from Mean Girls, the movie. The limit does not exist. So showing the limit as x goes to 0 of natural log of 1 minus x minus sine x, substituting 0 gives me 0. The limit on the denominator, 1 minus cosine squared x, also leads to 0. We'll apply L'Hopital's rule. The limit as x approaches 0 of the numerator, that would be negative 1 for the derivative of the inside, and then 1 minus x. Derivative of negative sine is negative cosine. Derivative of the denominator is 2 cosine x times negative sine, so that negative cancels the negative, and we have positive. And then substituting 0 everywhere, we're going to end up with, I believe, negative 2 in the top and 0 in the bottom. This is not indeterminate form. And just like in the movie, therefore, the limit does not exist. And then our final example is a graphic example. Let the function whose graph consisting of 2 line segments and a quarter circle shown in the figure be represented. We're going to find the limit at 4. So checking the numerator, the limit as x approaches 4 for 2g of x minus x at 4. Looks like we have 4, 2 as the ordered pair there. So that's going to give us 2 times the g of 4, which is 2, minus 4 is leading us to 0. So using that ordered pair, then the limit on the denominator as x approaches 4 of the sine of pi times 4. So the sine of 4 pi is also 0. Therefore, we can apply L'Hopital's rule. And by L'Hopital's rule, taking the derivative of the numerator is going to be 2g prime of x minus 1 divided by pi cosine pi x. And then we want to see what's the derivative at 4. And the derivative at 4, this is the graph of g. The derivative at 4 looks like the slope is 2. And we know that the cosine of 4 pi is going to be 1. So substituting 4, we got 2 times 2 minus 1 divided by pi times the cosine of 4 pi. So 4 minus 1, we have a limit at 4 of 3 divided by pi. And that, my friends, is indeterminate form.